I'm recording. Here we go. All right. Hello. Hello. This is if you missed 11.6 because of freshman retreat or anything else, this is a catch-up lesson for you. Okay. So our warm-up here was a piecewise function. We had to sketch this. So if we were to sketch this, you want to start at that breakpoint, which is -1, and plug it in. If we plug in -1 here, you'll get 4. Right. -1 squared is 4. -1 squared plus 3 rather is 4. So this is our point here, and it would be open. Say again. Okay. And then it says less than -1, so this is a parabola that's just going to continue to the left. Then on the above here, we're also going to plug in -1 in here. You're going to get -2 times -1 plus 2, and that's also going to be 4, which would also be an open circle here. But it's going to have a slope of -2 going down. So it's going to look something roughly like this. So this is what our piecewise function looks like. Now we're going to take a couple limits. So we can do limit of as x approaches -1 from the left. So as we come from the left, as we approach from the left, let me label this here. This is going to be -1, and this is going to be 4. As I approach from the left, what's the y value I approach here? I approach 4. So this would be equal 4. As I approach from the right, the limit is also 4. This is also 4. A little typo here. This should just be the limit overall. So if the limit from the left is 4, and the limit from the right is also 4, and the limit overall is 4. However, if we want to find f of -1, meaning the y value at -1, what is that? Well, it's an open hole at that point. So is the function defined at -1? No. So this is undefined. And that was the warm-up. Okay. So today we're going to move to the notes now. We are linking limits to continuity. So we're on 11.6. The definition of continuity. So before, when we talked about continuity, I think I just said to you, it's just when you pick up your pen or pick up your pencil. Like if you ever have to do that, that's like something that's discontinuous, which is true. But now that we have limits, we can write our discontinuity in a more formal way. So we can say that a function is continuous at an x value if a function is continuous at an x value if, and there's 3 conditions. 1, 2, 3. So number 1 is that the limit has to exist. So the limit as x approaches that a of f of x needs to exist. And remember, like, we know the limit exists if the limit as x approaches a from the right equals the limit as x approaches a from the left. So the limit needs to exist. The limit needs to be there, it needs to be a value, it needs to exist. 2 is that f of a must be defined. Right, so that means we have a y value at that x value. And 3, last part, is that the limit has to equal the output. So whatever that output was needs to be the same as the limit. These are our 3 conditions. Okay. So let's look at some examples on the right. We have different kinds of discontinuities here. This first one here, anybody remember this? The name of this one? This is a hole, or also known as removable. And so if we look at this and we think about the 3 conditions, we know this is discontinuous, but why? does the limit exist here at -2? So does it approach the same value? It does. The limit does exist here. Is f of -2 defined? Yes, it's here. But does the limit equal the output? No. So this would fail number 3. Does that make sense? Removable. So this fails number 3. This one right here, do you remember what this is called? We have here a asymptote, vertical asymptote. So this is called an asymptote discontinuity or asymptotic. So what does this fail? Does it have a limit? No. So it fails 1. Is it defined? And so does the non-existent limit equal being undefined? No, right? So it's fails all. So it fails 1, 2, 3. What about this one here? So this is called, I think I heard it earlier, this is called a jump. There we go, that's good. And so what does this fail? Does it have a limit, this at 1 here? Does it have a limit? Do they meet the same value from the left and the right? Does the high 5 meet? No. So it fails 1. Is it defined? Yes, there's a solid point. And so, but because it doesn't have a limit, it fails 3. So this fails 1 and 3. And then last one, number 2, this is also called a whole. For this one, does it have a limit? Does the limit exist here too? Is it the same from both the left and the right? If we squeeze on it? Yes. So it has a limit. Is it defined?
Yes.
Is it closed or open?
Open.
Anywhere closed? No, right? So this fails being defined. And so therefore it must fail 3 as well, because if it's undefined, it can't equal the limit. So this would fail 2 and 3. Okay? Does that make sense? The limit must exist, it must be defined, and the limit must equal whatever the output is. Okay? Good. So questions that you can come across here are like the one below. You can be given a piecewise function, this should just say b here, and you have to find this unknown value b that makes these two continuous. So it'll say what values of b would make the following function continuous, and it would say, usually it'll say at x equals 2, whatever point these are disconnected at. So to solve this, if it's continuous here, that means that both of these need to what? Both of these need to, if it's continuous at 2, both of these need to be the same what? They need to be the same value at 2, right? So it needs to be true that the limit as x approaches 2 from the left of g of x needs to equal the limit as x approaches 2 from the right of g of x, and it also needs to be true that this equals g of 2. If we want to be continuous at 2, these 3 things need to be equal to each other. So let's find them, right? So g of 2, you find that by just doing what? G of 2, you would just plug a 2 into which one here? The second, right? So to plug in a 2, you get 2 squared minus 2. That's going to be 4 minus 2 is 2. So this is 2. So g of 2 is just 2. The limit from the right. So which one of these is the limit would help me find the limit from the right? Which one of these is approaching from the right, if that makes sense? The top or the bottom? The bottom, because this is greater than 2. So this would be to the right. So we do the same thing. We're going to take the 2 and plug it in here to find that limit from the right. So we're going to get the same value, 2. So that means that the limit from the left has to be what? Limit from the left has to be 2. That means when I plug in a 2 into this, it has to equal 2. So what we're going to say is b times 2 equals 2. Therefore, b would have to be what? B would have to be 1. So that is our answer. I think like a really simple way to explain this is you got to set both of these equal to each other at this x value. So you could say 2b has to equal 2 squared minus 2 and then solve for b. That's a really simple way of explaining it. Okay? You're setting these two parts of the piecewise function equally to each other at this value. That's how you find out what b needs to be. Okay. Good? All right, next one is you're given a piecewise function. How do you know if it's continuous at 7? What would you have to do here? You'd have to do the same thing you did above. So you need to find the f of 7. You need to find the limit as we approach 7 from the right. And then we need to find the limit as x approaches 7 from the left. Okay. So f of 7, we plug it in. Would that be plugged into the top part or the bottom part? If I plug in a 7, is that going to go in the top expression or the bottom expression? Which one has 7 included? Top, right? So plug in the top, so it would be 3 plus root 2 plus 7. That's 3 plus root 9. That's 3 plus 3. That's 6. Okay. To find these two, the limit as we approach from the right and limits as we approach from the left, that's kind of the same thing as the left side. You are plugging in a 7 into the different parts of the function, just into either the top or the bottom. So if you want the limit as we approach from the left, that would be when x is less than or equal to 7. So that would just be this one, which we already found here. Does that make sense? So f of 7 and the limit as we approach 7 from the left are the same because they represent the same part of the piecewise. So again, this would just be the same thing. 3 plus root 2 plus 7. That's 3 plus root 9. That's 6. So these two are equal to each other. To find the limit as we approach 7 from the right, so this is x is less than or equal to 7. This is x is greater than 7. So because it's greater than, that's going to be to the right. That means we plug a 7 into this one here. So it would be 8 minus root 7 minus 3. That's 8 minus root 4. That's also 6. So because the limit from the left equals the limit from the right equals the output, this is or is not continuous. It is continuous. Okay? Make sense? Okay.
Wait, you said the output from the right matches it?
So the limit from the right and the left need to be the same, and also the output of the function needs to be the same. In this case, the output and the limit from the left were the same exact expression. So those were automatically equal to each other, but then we had to make sure that the limit from the left versus the limit from the right also matched. So the limit from the left and the output were the same expression, but we had to check the limit from the right. Essentially, like, what all it boils down to is plugging in this number into the top and into the bottom and making sure it matches and making sure it has an output at that value and that matches it. Good? Okay. All right. I'm going to keep lecturing so we can just do a big block of practice at the end. Okay, we're going to move on to our next thing. Go to your packet, the warm-up, and we're going to skip over page 2 for now. We'll come back to that, and we're going to go to page 3. We're going to look at this comic. Okay. So the second part of today's lesson, first part is defining continuity. The second part is called the intermediate value theorem. That's what IVT stands for. Intermediate value theorem. So let's think like what these words mean. Okay. Theorem, you have an idea. It's kind of like a rule, right? What is it? What about intermediate? If you think about something being an intermediary or intermediate, it's in the middle. Okay, so we got middle, we got rule, and value means value. It means value. What a value would be a number, right? Okay, so between number, rule. It's kind of what the intermediate value theorem is all about. Let's look at the comic. You guys already read it? You notice I used to be just as tall as you. I know how the intermediate value theorem works, Dad. Okay. I'm going to do you guys have an idea of what this is talking about just from reading this? Okay. Can I use somebody as an I need to use somebody as an example. Can I get a volunteer? Okay, Caden. So we're going to talk about Caden here. And in Caden, you're kind of going to be the dad of this scenario, okay? You're kind of going to represent him. So let's say we're going to talk about Caden's height. So I'm going to draw a little graph here. And this is going to be Caden's age. And I'm going to have essentially 0 over here on the far left, right, when he was born. And then, how old are you now, Caden? 16. That's going to be his current age here, okay? And this is going to be, let's call it h of t, and this is going to represent Caden's height. So on the left here, this is going to be height. And so how tall are you now, Caden? 6'1". So at 16 years of age, Caden is 6 feet 1 inch. So right here. And how tall do you think you were when you were born? Yes. A foot, right? I don't know exactly what we'll call it a foot. So down here, you're at 1 foot. Okay. So in this question, Caden is saying we can just talk about Caden and then somebody who's shorter than Caden. I used to be as tall as you. What is that saying? Well, we're saying that Caden, between being born and present day, Caden had to be all of the heights between 1 and 6'1", right? He couldn't skip any heights. He couldn't one day wake up at like 5'11" had skipped 5'10", right? That didn't happen. Even though we're growing very, very slowly, we have to be every single height between the height where we're born and the height we are now, right? So if we think about this curve, I don't know what the curve looked like. I imagine it looks like this. We're starting to slow in height growth as you get older, but he's still got room to grow. But that's what the intermediate value theorem says. It says that if you know a certain output is here and a certain output is up here, then you have to be all the outputs at some point between these two ages. Caden had to be all these different outputs. So a question could say, is there some value like C where Caden was 5 feet tall? And to that you would say, is this yes or no? Did Caden have to be 5 foot tall at some point? Yeah, then yes. But what if you said, is there some point where Caden had to be like 6 foot 2 inches, right? And to that you'd say, no, right? Because that's beyond what he has been. This is the intermediate value theorem. It says that if we have a function, we must be all the outputs between two separate outputs of that function. There is a condition though. So let's okay, let's talk about the condition before we move on. One thing I said there was that Caden couldn't skip any heights. He couldn't like jump all of a sudden. So what am I kind of referring to in a math term? When jumps, it has to be continuous. Exactly right. So a condition is that it has to be continuous. If it's not continuous, we can't use the intermediate value theorem. Okay. Good. Okay, so this is kind of the concept. Let's formalize that in your notes. You're on page 8 of your notes. Must have continuity. Okay, so these are the notes. So let's read this together. The intermediate value theorem, or IVT, is used to prove that a certain y value must exist or be defined for a certain function, right? So in this case, we're talking about like a specific height that Caden had to have. So we say, if a function f of x is continuous, that's what Addison just said, we have to have that condition that it is continuous on AB. Do you know what this means, like on AB? This means like on a range of x values. So in cadence terms, this would have been 0 to 16. That would have been what we would have written here. What we're saying is, because cadence height is continuous from 0 to 16 years of age, then his height hits every value between f of 0, which remember that was like 1 foot, and f of 16. And remember that was like 6 foot 2, 6 foot 1 rather. Do you guys understand the concept? Question?
Yeah. So basically the FC has to equal y.
The f of x has to hit every single y value between f of a and f of b. So if f of a is 1 and f of 16 is 6 foot 1, it has to be every single value, 1.1, 1.2, I mean every single value between 1 and 6 foot 1. The way that we justify using IVT, and like in calculus, the language we use is really important, and you'll see some like sentence structures here that we use. We have to be careful to verify everything. So the first thing you got to do if you're justifying using IVT, like if you want to say that he was 5 foot at some point, you have to say that it's continuous. So we have to verify continuity. That's number one. So usually that's given to you. Verify continuity is met. Usually that's told to you. Number two is you need to find f of a and f of b. Number three, you need to check that value, usually it's called f of c, is between f of a and f of b. And then four, you make conclusion. Right? So the sentence that you write is along these lines. I mean, it's pretty strict. You need to say, since the function is continuous on a to b, and f of a equals some value, and f of b is some value, the IVT guarantees that there is a x value c such that f of c equals m because m is less than f of b but greater than f of a. Let me zoom in on that. I'm going to walk through it again. So since the function is continuous on a to b and f of a is some value and f of b is this other value, the IVT guarantees that there is an x value, c, which is this over here, for example. This is the c, such that f of c equals m. M is the y value here, because m is between f of a and f of b. Like this example kind of clearly shows it. You have this a to b, so this is like what we're the domain that we're looking at. We look at what f of a is. We look at what f of b is over here. And so the IVT guarantees that all these values between f of a and f of b have to have been hit. So, for example, m, because m is between f of a and f of b, that's what we're saying right here, m is between f of b and f of a, there must be some x value c where f of c equals m. Does it make sense? Okay, all right. So let's look at an example here. The function h of x is continuous in the interval -3, 7, with h of -3 is 10 and h of 7 is 2. Is there a guarantee that there is some value a in the domain such that h of a equals 1? So in this case, like they're using a instead of c, but they're just saying, is there an x value where the output has to be 1? So the way I would approach this is I would actually do a little sketch, and I would plot these points. So negative 3 comma 10 would be like right here, right? That's that first point. And 7 comma 2 is like, we'll call that here. So this is negative 3, and this is 10, and this is 7, and then this would be 2. So we have to hit, if I know that this is a point, and I know that this is a point, that means I have to hit all the y values, all these y values. I don't know how the function looks, but all these values here need to be hit. Everything from 10 to 2. So is it guaranteed that there is a 1 between these two? No. Why is that? Why is 1 not guaranteed? Because is 1 between 10 and 2? No. So that's how you know. But if you said, let's do a different version, is there an A where h of A equals 5, would that be true? Yes, because 5 is 5 between 10 and 2? Yes. So the y value that we're looking for has to be between the two y values of h of A and h of B. So the sentence that you would write in this situation is, since, and again, like the sentence is really important, since h of x is continuous on, okay, what's my A and B? Continuous on what? We'll go here. What's my negative 3? It's right here. Negative 3 comma 7. Since it's continuous on negative 3 comma 7, and h of negative 3 is 10, and h of 7 equals 2, comma, the IVT guarantees that there is an x equals A such that h of A equals 5, since 5 is less than 10 but greater than 2. Oh, you can't see it. Okay. We'll keep practicing the sentence, guys. I know it seems really hard, but I know it doesn't have to be worded exactly like this, but you need to hit the key points. You need to hit that h of x is continuous. You need to say what h of A and h of B are, and then you're allowed to say there is an A such that the y value is between those two. All right, I'm going to end the video here.